Let me take it up to this. This tree can have any values. Here I'm not putting any constraint on the tree. Let's say 12, 97, 23, 4, 8, 6, 0. Even minus it can have -7, 18, 13. When I'm drawing this tree, I have used some random values. But when I'm drawing the tree, I have used something in my mind while drawing the tree. Yeah. What is that something that I have to keep in mind? I have kept in mind? Yeah, it is filled left to right. Each node has max 2 children, fair. Yeah. So one thing that I have kept in mind is, yeah, I have filled the tree, filled nodes or created nodes level by level. That is one thing. And second thing is they are filled left to right without leaving any gap. Without any gap. That means if I ask you to insert one more value, let's say 25, where will you insert that value? Yeah, it will be next to 6. That means it will be the right child of 4. Okay. Another observation that you're sharing that is not intentional, but yeah, that is what it became like. Let me make it 20. Okay. No, my bad. Yeah, I just wanted to wash away that notion. Yeah, I have not drawn left child to be less than the right child. That was not the intention. So thanks for sharing that, Sitaram. But that is not what I meant in this tree. Okay, so this tree is filled level by level, filled left to right without any gap. Such a tree which you always, where nodes are always created going left to right and level by level you go down. This tree is named something. Yeah, this tree is called complete binary tree. This is called CBT. Whatever definition we have written, that you have to fill left to right, so it's complete binary tree. So main intent is we do not leave any gap in between. And there is one more tree similar to this, which is called FBT. What is FBT? FBT is called full binary tree. Now, what is special about FBT? In FBT, the main condition is each node has 0 or 2 children, not less. And there is no condition about you have to fill left to right. Okay, is this making sense? Yeah. So full binary tree is a tree where each node has either 0 children or 2 children. Now, if I ask you, if I draw a tree here, is this a full binary tree? Whatever I have drawn, is it FBT? Whatever I have drawn, is that a full binary tree? Sitaram says no. Sitaram, why do you say no? Definition is in front of you. Is every node not having 0 or 2 children?
Sir, like it should fill from left to right.
No, that condition I did not write for FBT.
Okay.
FBT doesn't have that requirement.
Okay.
Okay. Now you will agree that whatever I have drawn on the right side is an FBT full
Yes, sir.
binary
Yes,
tree.
sir.
Yeah. So full binary tree is not necessarily a CBT, complete binary tree. Is every CBT a full binary tree? Not true, right? Yeah. So they are two different terms, two different things. Our focus is going to be on complete binary tree rather than FBT. But if I just ask you to still do some computation and do, if you have a CBT of n nodes, if I give you CBT of n nodes, can you tell me, not nodes essentially, yeah, if I give you a CBT of some height, if I fix height, I want to know from you what is the minimum number of nodes and maximum number of nodes with which you can create a CBT. And same way for FBT, what is minimum and maximum number of nodes. For example, if I give you height 1 and you have to draw a CBT, complete binary tree. If I say draw a tree of height 1, it should have only one level. What is the minimum number of nodes you need to create a CBT of height 1? Yeah, only one, because you will draw a root node only. And maximum? Maximum will also be 1. You cannot have more than one binary. If you are drawing a binary tree and height is fixed to 1, you cannot have more than one. For FBT, also can I say it is 1 and 1? Yeah. If I say you can draw a tree of height 2, if you can draw a tree of height 2, for CBT, what is the minimum number of nodes you need? Yeah, it will be 2, because you will draw this as CBT and minimum nodes 2. And what is the maximum in CBT you can have? If I say in height 2, yeah, maximum you can go to 3, right? Because this is a complete binary tree of 2 height. What about FBT? Minimum and maximum number of nodes. For FBT, yeah, for FBT it is going to be 3 and 3. Yeah, because if I give you height, you have to draw this only. There is no other FBT possible. Okay. What if I ask you to draw with height 3? Yeah, CBT will have 4 as minimum nodes and maximum you can go with 7. What about FBT? Yeah, for FBT, what is the minimum? Yeah, you have to go 3 levels. Is this an FBT? Is this an FBT, whatever I have drawn? No, that is not an FBT. Does root have 2 nodes? No. So I have to take one more node here to make sure the root has at least 2 children, either 0 or 2. So it is 5 and maximum 7. Okay. Now if I ask you to generalize it, if height is h, what you can give as formula for if height is h, what is the minimum number of nodes and maximum number of nodes you can have in CBT? CBT minimum 3. Oh, sorry, my bad. Yeah, it should be 3. Yeah, because in CBT we can have height 3, right? No, CBT will have 4, right? Not 3. Shiva,
Sir,
how CBT?
why can't we miss another child node for the root parent?
No, you cannot miss.
Just
What did
one.
it say? what did it say? It said you have to fill level by level. So this level
Okay,
without
okay.
you fill, you cannot jump, right? So it is 4 only.
Okay, okay, sir. Got it. Yeah, thanks.
For H, what will be the formula for minimum? What is your generalization? Yeah, 2 power H minus 1, and maximum is 2 power H and minus 1. Is that right? Yes. What about FBT? For FBT? Two power H minus 1 plus 1. Is that true or is that incorrect? Or it is 2 into H minus 1. Is 2 into H minus 1 working? Yeah. So this formula that we have doesn't work for height 1 max, right? Yeah, but in general, otherwise it will work. Yeah, so 1 is an exception, just ignore for 1. Yeah, so if it is reverse, if number of nodes are given, if number of nodes are n in CBT, then can I say height of CBT is going to be log n base 2? Will that be fair? Because this is maximum number of nodes in a CBT. Maximum number of nodes can be 2 power h. Then if nodes are given, if maximum number of nodes is roughly 2 power h, then h will be, take log base 2 of n, or let me put maximum number of nodes are comparatively this, then this is equal to h log base 2 of 2. Then height is nearly log n. Yes. Okay. So now let's focus on the CBT, complete binary tree. Imagine if I draw complete binary tree with some nodes. Is this a valid CBT? Is this a valid CBT? Yes. Let me fill some values. 11, 29, 40, 61, 30, and 90. Now, if this is CBT, can I just give them indices 0, 1, 2, 3, 4, 5? And can I represent this CBT also as an array? Because we are not missing anything in between. So what I'm going to do is I'm storing 11 here. I'm storing 29 here. I'm storing 40 here, 61 here, 30 here, and 90 here. Because there is no level miss, no gap in the CBT that makes it suitable to be stored it as an array. Is that fair? I can give you any CBT and you can store that as an array. The earlier CBT I had drawn, this will go to index 0, this will go to index 1, index 2, index 3, index 4, index 5, index 6, 7, 8, 9. I can take an array of size 10 and I can store these values in these indices. Yeah, guys, is this making sense? Yes. Now in this tree, just try to establish relationship between index of parent and its left child, parent and its right child. What is the relation you are seeing in the green indices I have drawn here? If you know the parent index, is it easy to find what is the index of left child? Is it easy to find what is the index of right child? So if I say to you, if parent index is given as PI, how can you find left child index? And how can you find right child index? What is the relation? How can you find LCI and RCI? Okay, so you are saying it is 2 times parent index plus 1, that is left child, and 2 times parent index plus 2, that is right child. Everyone agrees with this formulas? Okay. On the reverse side, if I know left child or right child, I want one formula for parent index. I want a formula, if you know the child index, doesn't matter it is left child or right child. How can you find the parent index using child index? Give me a formula for that. If I know the child index, I want to find the parent index. Irrespective of left child and right child, I want a single formula. Okay, Ci by 2 may not work. Mayuka, if you say 6 by 2 will give you 3, but it is 2. Yeah, but Ci minus 1 by 2 will work. Do a integral division. Will this be fine? From Ci, if we subtract 1, child index minus 1 divided by 2 will always give you parent index, considering it is integral division. 3 minus 1 by 2 is how much? Yeah, 3 minus 1 by 2 is how much? 1. 4 minus 1 by 2 is also 1, considering integral division. Yeah. Okay, so these formulas are interesting. If these formulas are known to us, is it easy to traverse? Is it easy to traverse this complete binary tree in top-down manner? Will it be easy to traverse this tree in top-down manner? If you know the parent index, you know how to go to left, how to go to right. Yes. Same way, is it easy and convenient to traverse this tree in bottom-up manner? Yeah. Is it easy and convenient to traverse it in bottom-up manner? Yes. That means if I just give you the array, if I just give you the array, you can traverse in either direction. You can move down to up and up to down, because you know how to jump from child index to parent index and how to jump from parent index to child index. Yes. Okay. So we have found one more way. If the tree is CBT, complete binary tree, then I can just give you an array and I can say treat this array as a tree and perform some operations on the tree. Using this array, if I ask you to fill, if I ask you to fill, not that, leave that aside. We'll come to another question. Let me take a CBT. Let me take little bigger CBT. Is this a CBT? Yes. Is this a CBT? Yes. How many nodes? How many nodes are there in the CBT? 10. Okay. What is height of this CBT? Yeah, 4. Roughly, can I say it will be in order of log n base 2. And roughly if you see, it is log base 2 of 10, and 10 is nearly 2 power 3. So ideally it is 1 plus that. When I say big O, can I say it's nearly 1 plus log n base 2? Big O wise, of course, we have mentioned it as log n. So 1 plus log base 2 of 2 power 3 point something, because 10 is 3 point something, little more than 2 power 3. It will turn out to be 4. Okay, so if we have a complete binary tree, let's say this is 70, this is 60, this is 40, this is 10, this is 20, this is 100, this is 46, this is 3, this is 91, and this is 16. So now you are seeing one tree drawn here. For this tree, if I have to draw a corresponding array and store all the values in the array, can you quickly do that? Draw this tree also, draw an array also. Yeah, and fill all these values that are there in the tree, fill all of them in an array. Okay, everyone drawn this? So you have a CBT which you have drawn as an array. Okay, now what our goal is, think about. I'm keeping a goal. We are going to modify CBT in such a way. We are going to modify CBT in such a way parent value is greater than or equal to both children. That means none of the child should be bigger than parent. Among children, order doesn't matter. But children must be smaller than parent. That is the criteria. Among children, no relation of values. But parent must always be greater than or equal to both children. Currently, whatever you are seeing in that, is every parent greater than both its children? Currently, it is not true. But we want to make this true. We want to restructure the values in this tree such that this property holds true for us. So what do you think? Where should we start to bring this change? What should be our starting point? Okay, we can go bottom up. Going bottom up is a good idea. Yes. Let's see. If we do bottom up, let's see what is the benefit. Bottom up wise, the last node is bottom up wise you are going. The last node is 9. Is 9 greater than both its children? Is 9 greater than both its children? Index 9. You very well know 9 does not have children, right? 9 is a leaf node. So can I say every leaf node is already meeting the property at parent level? Every leaf node is already in the state we want. Okay. That means we don't have to care about any leaf nodes. We have to care about whom then? Then we have to care about whom? The first known leaf node. So we have to start back with first known leaf node. Since we are going bottom up, can I say in array we have to traverse array backward? Because if you traverse array backward, you are actually going bottom up. Is that right? Okay. Yeah. Coming to first known leaf node, which is 20. Is 20 already bigger than its children? 20 has only one child, 16. 20 is bigger than its child already? Yes. Okay, so no action required at 20. Now come back to n, whose index is 3. Is 10 bigger than both its children? No. Then what should we do? Who should replace 10? Yeah, 91. And what makes you say 91? Imagine if I reverse. If 91 was in 7 index and 3 was in 8 index, then what will you say? Who should replace current parent if that is not the biggest? Then who should replace? Yeah, max of left and right. Okay. And if I ask you to do, rather than looking at tree and doing these operations, if I ask you to perform this on an array, we figured out that 4 is done. 4 is the first known leaf, coming to 3. Now 3 when you are at, who is the left child of 3? Who is the right child of 3? If you are at index 3, who is the left child? Who is the right child? Yeah. Left child is 3's left child will be at 6. No. Was it at 6? It will be at 7th index and 9th index. 7th and 8th index. Okay. Now you compare, if 3 is smaller than its children, at least one child, you have to find out who is the biggest among these. So biggest is 91. If biggest is 91, what you have to do? Yeah, you have to swap. So basically 91 should reach at the place of 10 and 10 should take the place of 91. So you have taken a bigger value down. Okay, fair. Now you go to 2. Who are the children of index 2? What indices are they at? Who are the children of 2? Yeah, 5 and 6. Among 5 and 6, which value is bigger? 100 is bigger. So you will swap 100 with 40. 100 will go here and 40 will go here. Yeah. So when 40 comes here, should we just stop here or we should also think about the children of 5? Yeah. Should we stop here or should we also think of taking 40 further down? We should also think of its children, right? Because in worst case, okay, just to bring that case in, I'm putting value 1 at the root because we will need that case. Eventually we will come to that point. I'm just changing root to 1. Okay, so far, what will be the first child of 5? if 5 had children, index of that will be 11 and 12, right? But that is outside the array. So 5 doesn't have children, so stop. Okay. Now coming to index 1. Where are the children of index 1? Children of index 1 are 3 and 4. Okay. Among 3 and 4, just see the values are 20 and 91. Who is the bigger value? 91. Okay, so 91 should replace 60, and 60 will come here. Now 60 has come to index 3. Who are the children of 3? Children of 3 are 7 and 8. At 7 you have 3, at 8 you have 10. So this is already bigger than them. 60 is already bigger, so we don't have to take it further down. Okay, so this is fine. Coming to index 0, the value at index 0 is 1. Now, where are the children of 1? Sorry, where are children of 0? My bad. Yeah, children of index 0 are 1 and 2, which is 160. So 1 should swap with 100. 1 comes here. So 1 came at index 2. From index 2 also we have to make sure it goes down. The children of 2 are at which index? 5 and 6. Okay. Among them 6 is bigger. So 46 will replace 1. Then we reach 6. We look at children of 6, but we figure out that 6 children are outside the array indices. So we are done. So whatever changes we have done now, if I make these changes to this tree also, then at root we have 100, then we have 91, then we have 46, then we have 60. After 60 we have 20. After 20 we have 40. After 40 we have 1. Then we have 3, 10 and 16. Now you see whatever this tree is looking like, here this property is holding true. Here this property is holding true. Okay. And this tree is good for visualization, but we have done everything on array. Whatever operations we have done on array. Yes. Now if I just show you this array and ask you, where is the maximum value in this array? Where is the maximum value in this array? At which index? You have maximum value at index 0. So if I ask you to get a maximum value from this array, what will be the time complexity of doing that? Constant. You'll just say return a of 0. Okay. Now if I ask you, whatever this tree is, whatever this structuring happened, I want you to insert 49 as a new element, or rather than 49, let's say, let's say in this we want to insert 105. If 105 has to be inserted in this tree, where will that go? If a value 105 I want to insert in this tree, where will that go? No? Like initially, if I'm inserting as a value, right now don't worry about the restructuring property. If I have to insert, it has to be inserted here, right? It will be at index 10. That means if I have to do this operation of insertion, I have to add one more thing. I have to increment my list size and I have to put 105. Now after putting 105 here, our property got violated. So how can I make sure my property of parent being bigger is still maintained? What should I do now? What should be done now? Yeah, check with parent. That means from index 10, I have to just go bottom up till parent, parent, parent. Is that clear? And I have to continue doing swaps. Okay, current value is 105, parent is 20, so swap. 105 goes here, 20 goes here. Then parent is 91, child is 105, swap. Then parent is 100, child is 105, swap. Inserting a new value after everything was properly in the shape takes how much time complexity? Yeah, how much time complexity? Height of the tree, and what is height of complete binary tree? Log n. Okay, so that is our second operation, which we are saying we want to insert a value x. So what you do is you append it to the end, append at end of A, and then adjust bottom up wise. Go bottom up and adjust bottom up and adjust last index value, last inserted value. This can be done in log n time. Okay, getting max is constant time. Inserting is log n time. Now imagine I want to delete maximum value. What is the maximum value in this tree? What is the maximum value in this tree? Yes, 105. I want to delete it. I want to get rid of it. And after that also I want restructuring to happen. Now, because it is an array, in array, this is the dynamic array like a vector or list. Which element deletion is most efficient? If you have a dynamic array, which element can you delete efficiently? Last. Okay. First is not efficient. Last is efficient. So that means I can get rid of last element easily. That means 20 can be removed easily. So what we do is we use a trick. We first replace 20 here. So we move 20 here. After 20 moved there, we delete it. We remove it because removing it is easy. Now whatever tree you are seeing, who is violating our property? Who is violating the property? 20. So what we should do? We should take 20 and we should go top down and we should adjust 20 at its correct place. Is this making sense to everyone? 20 should land up at its right place, correct place. So 20 compare with both children. 20 is left child is maximum, so 20 comes here. Now again compare 20 with both the children. This is 91, this is 60. So 91 takes over, 20 goes here. Now again compare 20 with 16, right child is not there. So 20 landed up at right place. So can I say when you are deleting, you are going top down? So we are saying delete min. And we have to return also. So eventually, what did we do in delete min? What was the first step we did? We copied a of n minus 1 to a of 0. Is that fair? And then what we did? Oh, sorry, delete max, my bad. Yeah, thanks for pointing that out. We are deleting max. Then what we do? We go top down. Sorry, before that we remove a of n minus 1 from list. So list size reduces now to n minus 2. And then we say top down to adjust a0 to correct place. How much time will this operation take? How much time will this operation take? This will also take log n. Where did we talk about these three functions? get max, insert, and delete max. Did we talk about these functions earlier? Where did we talk about these functions? In this table, what data structure we said provides these functions? No, stack never provided us delete max. Stack gave us max, but not delete max. In this table, that means whatever we were discussing right now, that was just implementation of max priority queue. Is that clear? Whatever we discussed right now, it was just a definition of max, or you can say implementation of max priority queue. Yes. So implementing max priority queue internally, what do we need? If we want to implement max priority queue internally, what is it that we need to implement max PQ? We used array only, right? Yeah, we visualize it like a tree, but array is able to do this magic. Yeah. So now our goal is to implement this class, call it max PQ. Internally, you know, you need a list. Internally, you are needing a list of it. This is your array that you are managing internally. And the functions we want to implement are insert, then next function you want to implement is, I'm writing it side by side so that implementing them becomes easy. Get max. We can call this function as get only because we are calling it max PQ already. And third is delete max. Its purpose is to just delete the maximum value. And if we, along with it, if we have to support one more function, which is size. Okay, get function returns the max. So how will get function be implemented? Keep in mind, this is our array. This array is CBT. Yeah. So for this, you have to just return A0. It became constant time. For size, I can eventually put size here only. For size, what we will return? A dot length or A dot size, depending on the language. If I have to implement is empty also, or bool empty, bool is empty. That can also be done based on size. Return A dot size, not A dot size, sorry, this dot size, double equals to 0. Okay, this we are clear. Yeah. Now I want you guys to implement insert and delete max. And keep in mind when you're writing that, you will have to write top down and bottom up functions. Take some time and move around in the array and implement First implement insert. Just see what we are going to do in insert. I want you guys to translate this idea to code. Yeah, so get started. Because what is the first step we have to append at the end of A? So in insertion, what is the first thing we have to do? Again, depending on the language you use, let me just call it add function. What will this add do? Yeah, add will append at the end. Okay. Now which index is something that we want to balance out or that we want to take top down and fix it? No, wherever you inserted, this is a violator, right? Imagine here if I go and insert here, let's say 50, this is the index that needs to be taken up, right? Yeah. So we have to fix the last index. Now one is I can write the complete code here, but I'll prefer writing that as a separate function. And our goal is to take it up. So I can call it bottom up, fix bottom up heapify. So whatever notation we are talking about, it is actually a heap. And I want to heapify the index a dot size minus 1. This index needs to be readjusted and properly fixed. Sometimes people call this bottom up as, they call it heapify up. We have called it bottom up. Okay. So now coming to this BU heapify, bottom up heapify. Array is already available as a data member. So we are fixing it on some index C. Okay, so how do you move it up? Again, we think of writing a recursive function. If you are at index C, how do you find its parent? How do you find the parent of C? We talked about formula. We said C minus 1 by 2. Okay. So you want to compare current value with its parent. And when will you swap? When will you decide to do swap? So when the swap has to be performed? Yeah, if child is greater than the parent. Otherwise, you will be done, right? Yeah. So only case we will make recursive call is if child index value is greater than a of pi, then what should be done? We should perform a swap. You will swap these two values, and after swap, can I say you will continue going up to heapify the parent index? Is that right? Okay, this I have to say child. I use C. Is that fair that after swapping you will again go up and heapify? And when will this entire recurrence stop? Where will this recursion stop? I guess when will you not find the parent? Yeah, if C is 0, you will just say stop. If you have reached the root, you're done. You don't have to compare root with its parent. Yeah. Is insertion making sense to everyone? Okay. Now, if insertion is clear, quickly complete deletion also. And for deletion also, when you write heapify, you write it separate function. Okay, what if we have duplicates? Okay, good question. Sitaram, even if we have duplicates, let's try to see. Now let's gradually build our heap. First value, let's say, was 100. Now, if I insert 90, do you need to heapify 90 up? Is it required? Does 90 need to go up? Yes, Sitaram. No. Let's say now I insert 40. 40 also doesn't need to go up. Okay. Now, if I insert 90 again, now tell me what will you do? 90 is not greater than its parent. Will you really try to take it up or you will stop? No change? Yeah. So if you see when you have duplicates also, it is already, see, we are swapping only when child is bigger than parent. If child is equal, we don't swap. Hope your question is answered here. Yeah. Okay, so duplicates do not matter. We can still insert duplicates in priority queue. Yeah. So for deletion, what is the first thing you will do? When you have to delete a value, what is the first thing you will do? Will you swap or you will just copy? Just replace. Will replace, right? No swap. Anyways, maximum is going to be deleted. So why care about swapping? A of 0 will be swapped with A of A dot size minus 1. You're just copying the last value here. Is this clear? Avinash, Veena, that swap is not necessary. Even if you do swap, it is okay, but why unnecessary take this value down? Okay. After this, what do you do? After this, you remove the last index. Usually, lists sometimes give remove last function. Like in C++, vector has pop back, Python has pop. Yeah. So let's say remove last, we'll just get rid of the last. And it will also change the size. Now you have to do top down heapify. Let me call it TD heapify. You will do this on which index? From which index you want to start top down? Yep, it has to start from index 0 because 0 index is what we have copied and made corrupt. So now the expectation from you is to write function. You have to write TD heapify. And you have int some index I. Your goal is to make sure that if I value is, if A of I is smaller, then it should percolate down. Yeah. So implement it and let me know once you are done. Once this is done, our heap implementation is completed. Yeah. So what will you do at index I? What is the main goal? Okay, you have to find. Okay, you will compare it with left child and right child. So can I say, let's take left index as 2 into I plus 1. Let's take right index as 2 into I plus 2. Now our goal is to find out who is maximum. And of course, you also have to compare with A of I. So can I say you have to find out which out of 3, I, Li or Ri, out of these 3, who is maximum? 3 possibilities are there. First, I can be maximum. If I is maximum, what will you do? If I is maximum, what will you do? If A of I is maximum, you will do nothing. You will just stop. You will say, hey, I'm done. I don't need to heapify down, right? If Li is maximum, what will you do? If left index, if A of Li is maximum, what will you do? You will swap A of I with A of Li and you will continue heapifying left index. Is that right? Is that correct? Otherwise, if right index is maximum, you will swap with A of I, Ri. A of I will be swapped with A of Ri. Okay. So first goal is let's find out who is maximum. Let's assume I is maximum. Now, Mi will be one index which will track who is maximum. Li is maximum, Ri is maximum, or A of I is maximum. So first, how do I compare it with left? If can I say if A of Li is greater than A of Mi, then Mi is equal to Li? I'm saying if left value is greater than current max, we assumed I to be the max. Same way, can I say if A of Ri is further greater than A of Mi, then of course Mi has to be Ri. All I'm doing is in these two conditions, I'm trying to figure out Mi is Li or Ri or I. Is that fair? Now, if Mi is not equal to I, that means either left or right is maximum, I'll perform a swap. You will swap A of Mi with A of I, and then you will say TD heapify of Mi. Is that correct? Yes. Is this making sense? This is just one way of writing code. It can be implemented in another way. You may have written different. This is also recursive, but terminating condition is not there because this else case is a terminating case for us. When I is Mi, we are not proceeding. If you really see in that case, recursive call will not happen. Yes, very good point. Krishna has raised a point here. Imagine this is 90, this is 30, and now, or let's say this is 30, this is 90. This is I. Does this I have right child? If imagine this is just two nodes, do we have right child for I? No. That means here, this line that I'm performing, if imagine this is index 0, this is 1, and this is 2, then what will happen in this line? If I try to compare A of 2 with A of 0, what will happen? It will give runtime error because I'm accessing an index which is outside the bounds. Yep. So we have to fix this issue. because we are blindly assuming that every I will have left child also, right child also, which is not true. It is not a full binary tree where if children exist, both are there. So how do we fix this? Yes, this is a bug. So before accessing, we have to put a check. There should be a condition here. What should be that condition? It should be rewritten as can I say if Ri is less than a dot size and then a of Ri is greater than a of I. If I make this change, will this be fine? Will this be fair? Will we be able to avoid? We will be able to avoid that runtime error. Because I should not be touching a of Ri if Ri is not less than a of size. Here, my array size is 2. My 2 is not less than array size. Is this clear to everyone? Only if first condition is true, it will go and compare second. Do we have similar problem here also? It is possible that a node may not have left child also. Okay. So go ahead and fix this code. Yeah. Make sure you write the condition here. Yeah, what will be the condition then? Yeah, what is the condition? If Li is less than a dot size and a of Li is greater than a of I, only then update Mi. Yeah. So basically this TD heapify is important, that here chances of making mistakes are there. This issue was not there in bottom up, because if child is there, parent will always be there, except root node, and root node became our base case. Okay, are we good? Are we clear with this? Yes. So we have implemented what? We have implemented max PQ. Imagine if I want to change it to implement another class min PQ, what will be the change? Rather than max PQ, if I was implementing min PQ, what will change? That means every time I insert, I will have to do bottom up PP5. But this time when I'm comparing, yeah. So only thing that is changing is if condition. That means the change has to happen only here and here. That this if case, this if case, and this if case. We are comparing only in these three places. So here the change is this greater than will become less than. That's it. So if I can take this comparison function out, if we can take this comparison function out, compare two values, a comma b, and make it a Boolean function. And if I change it to use that comparator, that means I can implement same class I can implement same class to act as priority queue, be it min or max. Comparator will decide how I write comparison function, that will decide it is min priority queue or max priority queue. So it's the comparator who is making the decision. And we learnt about something similar where comparator was the deciding factor. Where did we discuss this already? That take comparison out, write comparison. We did it in custom sort. Yeah. So whatever comparator you use in custom sort, same comparator works with priority queue. So in the language in which you code, if you have done custom sorting already, using min priority queue, max priority queue will be easy. You just have to implement your custom comparator. So basically the point I'm saying is, in your language, you should figure out how you can use a built-in priority queue. What comparator you have to write if you have to make that work as min or max priority queue. In C++, by default, priority queue is max priority queue. You write custom comparator. There is a built-in comparator also available to make it min priority queue. In Java, by default, priority queue is min priority queue. And you use a built-in custom comparator to make it work at max priority queue. Okay. Yeah. So we got introduced to all three: queue, double-ended queue, priority queue, stack. Going forward, we may see questions where we may apply them. They may become one of the solution for the problems we discuss in future.